learning video D of section 2.4. Again, we've got a situation here where we're going to have to use the product rule for this piece of it. This factor times this factor, but when we take the derivative of this factor, we've got now a quotient to take. We'll have to then evaluate it at a specific point. So let's begin finding the derivative. And the first thing we're going to do is the product rule. I'll just write that up here. So the product rule. So we have the first factor times the derivative with respect to x of our second factor plus our second factor times the derivative with respect to x of our first factor. We're showing all of the derivatives we're going to take at first, and we have more to show, so let's continue on. We have the factor of x plus 5 divided by x minus 1 times the derivative of 2x plus 1. The derivative of 2x is simply 2. The derivative of 1 is 0. Plus, we're at the plus sign here, the factor of 2x plus 1 times the derivative of, and this is a quotient, so now we're going to have to use the quotient rule on this part. So we have our denominator times the derivative with respect to x of our numerator minus our numerator times the derivative with respect to x of our denominator, and all of that will be divided by x minus 1 quantity squared. Okay, these become a little bit involved, and the more you do them, the easier they will become. We have x plus 5 divided by x minus 1 times 2 plus, we're at the plus here, 2x plus 1 times, and we have our x minus 1 times our derivative of x plus 5. Derivative of x is 1, derivative of 5 is 0, minus x plus 5 times the derivative of x minus 1. Derivative of x is 1, derivative of 1 is 0, all of that divided by x minus 1 quantity squared. Okay, at this point we showed all of the derivatives we took here. We actually took the derivatives at this point, and now we need to show at least 2 fraction lines. Believe me, it's going to be more than that, but let's see what we have. We've got 2 the quantity x plus 5, so I'm going to go ahead and write that and divide it by x minus 1 plus, and I have 2x plus 1. I'm going to do this in a little work here before we get started here. Here's my x minus 1 minus, this is where we need to be careful of those subtractions, minus the quantity x plus 5, all of it divided by x minus 1 quantity squared. Now keep in mind, you cannot cancel the x minus 1's yet. This x minus 1 is not a factor, it's not something multiplied to everything in the numerator. But let's see where we can go with this. Equals, I do notice though that I have x minus 1 here and I have x minus 1 squared here. I could change this. I can have a common denominator if I make this 2 the quantity x plus 5 times x minus 1, and that then will give me x minus 1 times x minus 1, or x minus 1 squared, plus 2x plus 1 times, And if I very carefully work through this, I'm going to have x minus 1 minus x minus 5. So my x's will cancel, and I have negative 6 divided by the square of x minus 1 quantity squared. Okay. I'm going to multiply these together. So this would be x squared. Let's see, outside is negative x, inside is 5x, so that would be plus 4x minus 5. So that's going to give me here 2x squared plus 8x minus 10, multiplying the 2 through there. And over here, multiplying a negative 6 would be negative 12x minus 6. And since both fractions now have the same denominator, I'll get that. And I can simplify this then as 2x squared minus 4x minus 16 divided by x minus 1. And there's no reason not to. Let's factor out the 2x squared minus 2x minus 8 divided by x minus 1 quantity squared. I see no way that we're going to be able to factor this and get an x minus 1 squared, so we're kind of stuck right there. We're going to stop. But are we done with the problem? Let's go back. It said find the derivative at the point 0, 5. So let's see. At the point 0, negative 5, f prime of x, or the derivative of, and again, let's just remind ourselves, this is our derivative up here. So this would be f of 0 would be 2 times negative 8 divided by negative 1 squared. If x is 0, we have only negative 8. X is 0 is just negative 1. So I have negative 16. This is always positive, so I end up with negative 16. Now, let's check this one and see. Let's just make sure that we have this correct. And how do we check it? That's right. Let's go over here. I'm going to ask you to go to Document and Insert and New Problem. For those of you on the gray touchpad, just go home. If you go home and pick up, I'm sorry, let's try that one more time. I'm going to go to Current here. Let's do Control Home and then Insert and New Problem. Okay. So let's go to our problem here, and we're going to insert. Again, go back to the original problem. I cannot emphasize that enough. So we're going to start with a fraction. So we'll have a fraction, and the fraction begins with x plus 5. And then we're going to divide that by x minus 1. Move outside of that fraction, multiply, and give yourselves a set of parentheses, and we now have 2x plus 1. And we're going to graph that. We want to know the derivative at the point 0, negative 5. I'm going to change the window because negative 5 is way down here. So I'm going to change the window so I can see this a little better. There we go. And I'm going to make this, we can keep it negative 10, but I'm going to change this then to 5, and I'm going to scale by 1. And I'm going to make my negative, about a negative, maybe a negative 10 would be sufficient. And my input, my output maximum, I'm going to make that a 5 and scale by 1. So let's see how that looks. That looks a little better. You know the routine. Let's go put a point on the curve, and we'll put a point on right about there. Now, it looks like I could probably just use those coordinates, but just to be on the safe side, make sure that you actually type that in, just to make sure. It could be off a little bit and we wouldn't be able to pick that up. Go down and let's put a tangent at that. And I'm going to extend the tangent arrow so I can see that. And I'm going to measure the slope. Let's see, go down to measurement here. Measure the slope of that, and my measure of the slope is negative 16. Is that what we got? Let's go back down and check. And sure enough, it is negative 16. So our answer is correct. Okay, this is part 4, video D of this section 2.4. This problem is one again of our application problems, one that we're going to be able to see, maybe something you can relate to in your business courses. Finding the prices per pound of lean and extra lean ground beef from 1998 to 2005, modeled by this function. Again, I don't know who designed this. I can tell you though that they looked at data, they looked at a scatter plot, and they determined that this function actually would best predict the prices, PSR output, the prices of the lean and extra lean beef with an input of time. Time is between 8 and 15 years. T is the year, with T equaling 8 corresponding to 1998. Now we're asked to find dP dt. Be very careful when you read this. We're looking at the derivative of the output variable P with respect to the input variable T. So we're looking for the derivative of this function. Obviously, we're going to have to use the quotient rule because we do have a quotient for our function there. So find the derivative and then evaluate it for these 4 years and then interpret the meaning of them. So let's start with the first part of it, and that is, let's find the derivative of our output variable, our function P, with respect to our input variable T. This is where we are going to definitely need to use our quotient rule. So we're going to start with our denominator, and we will write that as carefully as we can. Make sure we get all of those digits in there. Times the derivative with respect to T of our numerator, and this should be a decimal point here, not a comma. Obviously, I've run out of space, so I'm going to have to say, continue it down here, minus our numerator, which is, because I've run out of space, let me just do it this way. And I'll just erase all of that, and we'll start again. Let's just say that we have our denominator. I'm just going to do this. This is my denominator. Times the derivative with respect to T of our numerator. Minus our numerator times the derivative with respect to T of our denominator. All of that divided by the square of our denominator. Now, I wouldn't normally do this, but I do want to get all these numbers in. Okay, so, and if you show me this, if by chance I would give you one with numbers, and of course you can write smaller than I can on my board here. We have our numerator, our denominator, and 1 minus and so forth. I'll try to write smaller here. times my derivative of the denominator, of the numerator. The first term is going to be 0. The second derivative of the second one is just going to be negative 0.2079. Remember, it's going to be t to the 1 minus 1, so we lose the t, plus 3, that's our exponent, times 0.00673, and that, oh, excuse me, that is a 2, so let's make sure we write that as a 2. So it would be 2 times 0.00673t minus, I'm still going to run out of space, aren't I? I'm just going to put this down here. This is my numerator. And the derivative of my denominator is going to be negative 0.1282 plus 2 times 0.00434t. Even with that, it's hard to get all those digits in. Okay, and so we'll just say the denominator squared. You know, this is one where, do I expect you to multiply all those out? On a problem like this, I would expect you to show me that you understand all this, the quotient rule. Writing all of this out, I understand, can be a real difficulty. So let's just, you can practice on the Inspire if you wish, but let's just go ahead and find out what our final answer is. Okay, what I did when I had this paused was I went back and made sure that I had everything in here correctly, and I also went into the Inspire, and as you can see, I have defined this function. This is one of those that you definitely want to define the function. If you remember, you go into Menu, Actions, and Define, and that then is going to save us from having to write this again. So, and again, I could have written this as P equals, but because I might want to look at it on the graph, I did it as F1 of X. So let's go into Menu and Calculus and pick up a derivative. And because we may want to graph this, we'll continue with the X. Tab, and then all we have to do is say F1 of X. And press Enter. So there is our derivative. Now, if we did it out by hand, we should still get the very same thing. If you did it by hand, you can check your work against this to make sure that it is correct. Now let's go back to this. It says evaluated for t equaling 8, 10, 12, and 14. On a problem like this, I am more interested in your ability to interpret the meaning of these values than I am in your ability to multiply with numbers such as this. So what we're going to focus on now is, given this derivative that we have found over here, if we look at this value at a point, and let's go into Menu. Let's go into Menu and go into Calculus, and we see this, it says derivative at a point. So we're going to have the variable x, and the value, now one of the values that we're looking at is 8, which is corresponding to 1998. And so we'll make 8 here, and we're looking for the first derivative, and our function is going to be f1 of x, and our value is 0.085426. So let's go ahead and write that for us. We'll just put dot, dot, dot. Let's go down here and say dp dt at t equaling 8 has a value of let's check that again, 0.085 0.085,426. Now, we get an answer, but the most important thing is, what does it mean to us? So if we go back here, the prices P of lean and extra lean beef modeled by this formula where T is year. So what we're saying is that the prices increased approximately and it doesn't tell us a unit here, so we'll talk about in a, I would assume it's in a dollar sense here. For each additional year when T equals 8, or in 1998. So all we can say is that in 1998 the prices of the beef were increasing approximately this much per pound. So we can say per pound on this for each additional year. How does that compare with, let's just jump to 14, okay, which would be 2004. So in our work here, we'll evaluate this at T equaling 14, and let's go back to our Inspire. We'll just jump up and grab that again, change that value to 14, and we see then that the prices per pound were still increasing, but they weren't increasing as fast. And so it's 0.00172, so 0.01732. So in 2014, prices increased approximately 0.01732 per pound for each additional year. It's these explanations that are much more valuable to our understanding than anything else that we can think about. Okay, very quickly before the time runs out, if we talk about this problem, where does it have a horizontal tangent line? If it has a horizontal tangent line, the slope is 0. So we would have to first take the derivative of this function, and it would be x squared plus 1 times the derivative with respect to x of x squared, x to the fourth plus 3, minus x to the fourth plus 3 times the derivative with respect to x of x squared plus 1, all of that divided by x squared plus 1, quantity squared. Again, I don't want to run out of time on this and start a new one, so we'll just get as far as we can, and then we will have to maybe come back on this. Derivative of x to the fourth is 4x cubed plus 0 for the 3. X to the fourth plus 3 times the derivative of x squared is 2x plus 0, and all of it is x squared plus 1, quantity squared. Now, we want this to be set equal to 0 to find our horizontal tangent line. When you think about a fraction set equal to 0, can the denominator ever be the 0 factor? And the answer to that is no. So we can only set our numerator equal to 0, and we would have to then solve this. Let's see, this would be 4x to the fifth plus 4x cubed minus 2x to the 5th minus 6x, and 0 is 2x to the 5th plus 4x cubed minus 6x. We can factor out an x, solve it. I leave this for another time so we don't have to start another video. I'll see you next